All right, we're going to do a retrosynthesis, and we're told that our final product is a ketone and an aldehyde. We're also told that we start initially from a cyclohexane. So let's see how we can come from a ring to a linear molecule like a ketone and an aldehyde. Right? Now, if we started with a cyclohexane, that means that we had a ring with 6 carbons. Well, let's count the number of carbons in this ketone. We have 1, 2, 3, 4, 5, 6. Okay, so we can kind of stitch together this ketone again and form a 6-membered ring. If we think about what reactions can break a ring into a linear molecule like this, especially one that forms these double bonded oxygens, all right, the best choice is probably going to be ozonolysis. So I'm going to try ozonolysis on this and see if it works. All right. Now we know that ozonolysis breaks a ring apart where it has a double bond, but we want a ring with 6 carbons again. So let's try to see if we can stitch together carbon 6 and carbon 1 into a ring and see what that would look like. If that were the case, we would get, again, a 6-membered ring. I'm going to label some carbons on it, so I'm going to label all 6 of these. And we know that if ozonolysis was done and I broke it at 1 and 6, that the carbons between 1 and 6 must have had a double bond. Right. So now I have 6 carbons here, I have 6 carbons here, but actually I also have an aldehyde. So I have a 7th carbon here. Let's try to figure out where on the ring to put my 7th carbon. Well, if I performed ozonolysis, it wouldn't just break this double bond, it would break all of the double bonds. And we see here that we have a doubly bonded oxygen at carbon 5. So if I went to carbon 5 and I add a double bond there, I would see that here I would break this double bond, I would form this doubly bonded oxygen, and I would also form an aldehyde here. So this is the molecule that after I performed ozonolysis, I got my product. Let's try to figure out the step that goes before this. So I need to figure out how to come from a cyclohexane, which has only single bonds, to a ring with double bonds. Okay. To come from single to double bonds, a good option might be elimination. And let's choose E2 elimination so that we can avoid any kinds of rearrangements. Let's take a look at this double bond right here. We can get this double bond if we did an E2 elimination. Either, let's see, if we had a bromine here, or if we had a bromine here. Okay? In either of these cases, technically, if I did elimination, I could form a double bond here and here, which would give me the product that I want. But if I use this to do the elimination to get this, I could also form a double bond right here, which is not the molecule that we're looking for. And we'll see for other reasons also why I want to put the bromine on that atom, or on that carbon. Right? So we've decided that we want the bromine in the vinylic position. So I'm going to go ahead and draw that. I'm going to put my bromine here. And I'm going to do elimination to form this double bond. So what kind of compounds could we use to get elimination? Well, we need a strong base. So I'm going to use sodium methoxide. I'm going to put it in ethanol. All right, and since this is a secondary alkyl halide, it could also do substitution, since this is a strong base, and it can also work as a strong nucleophile. So to guarantee that it's elimination, I'm going to add some heat. And this would give me elimination to form that double bond, and only that double bond. It can't form a double bond here, because that would make this carbon have 5 bonds to it. So it only has that one choice. All right, so now we know how to get to there. Let's try to figure out how we even got this bromine in this position. We have several radical reactions to choose from. We could use NBS, we could use bromine, so Br2, or we could use a halide, meaning HBr. Well, HBr would destroy this double bond, so we don't want that. If we just added bromine, Br2, with light, it could add to any of these carbons, since all of them are secondary. But if we use NBS in peroxides and light, we know that this only creates radicals in the vinylic position, meaning it would have to be on the carbon adjacent to the carbon that is doubly bonded. So if that's the case, we could get to this from this molecule. We add NBS with peroxides and light and would only put a bromine on either this position or this position. But since this is a symmetrical molecule, it's the same either way. Okay? We're getting closer and closer to the cyclohexane that we want. Our last step now is just to figure out how did we get this double bond right here. So we need to figure out how we basically came from a molecule with a single bond there to a double bond there. Well, we know again that we can form double bonds using elimination. So if I'm going to do elimination to get there. Here's my hexane. Here's a single bond coming off of it. Okay. I need to figure out where do I want to put the bromine. Do I want to put the bromine in this position, or do I want to put the bromine in that position? Well, if I put the bromine on the end here, on the methyl group, it would look something like this. The problem with this, is that this bromine is on a primary carbon. It's on a primary position. And elimination prefers highly substituted halogens. All right, you could do an SN2 on this easily, but we're looking to do an elimination. So we probably want to put the bromine in a more substituted position. So we're going to choose to put the bromine here. Here we have a tertiary halogen, which is easy to do elimination on. Now to do elimination, I need to choose a strong base. Okay. But we have a problem here. If I put my bromine here, okay, I can form a double bond on the methyl group, but I can also form a double bond on the ring itself using elimination. And in fact, Zaitsev elimination would want to put the double bond on the ring itself because it's more substituted. It's a more substituted double bond. It's a more stable molecule. So how can I force this to do Hofmann elimination? Okay. We do Hofmann elimination when we have a large, big, bulky base. So I want to do E2, I need to choose a strong base. I want to do Hofmann, I need to choose a bulky base. I'm going to use tert-butyl. Sodium tert-butyl. Alright, so here we have a strong, big, bulky base that's going to force our tertiary bromine to come off and to form a double bond on the least substituted alkene possible. All right, and we're kind of at our last step. We now need to figure out how did we come from something with no functionality, so just a cyclohexane, and we now know that had a methyl group coming off of it. And how did we put that bromine in there? Well, if we put a bromine in, it's actually coming to the most substituted carbon. How could I put a bromine to the most substituted carbon? I simply add Br2 and light. And that would be bromine in this tertiary position. Right? So let's just go through this in the forward direction to make sure that we did it right. We start with a methyl cyclohexane. We add bromine and light, do a radical reaction, and put bromine in the most substituted carbon. Then we do a Hofmann elimination, and we form a double bond on the least substituted place. Then we add peroxides, NBS, and light, and that adds bromine in a vinylic position, so on the carbon next to the double bond. Then we do another elimination. This time we don't use a big base, and we form a double bond here. And it can't form a double bond here again because this carbon already has a double bond. And how do we break this apart into the ketone and aldehyde? Through ozonolysis. And that's the retrosynthesis.